Okay, let's get going for the last talk of the day and the third talk of the short point methods session. Our pleasure to have one of the organizers of the whole thing, Aleksander, crash course.
Sure. Thanks, Ben, and hello, everyone. So let's start with some admissions. So essentially, I was thinking quite a lot what to talk about, and my first instinct was, of course, to say what is the latest and greatest and most advanced that I can say about interpret methods. But then I realized, I look back to, how I struggled like 7 years ago or something when I tried to get into continuous optimization as a theory student, and somehow the problem I had there was that there's a lot of sources to read about continuous optimization, and some of the authors of the sources are here. Except the problem I had was that each of the source develops a different perspective on a given building blocks, but somehow it's a little bit hard to draw connections between these different building blocks. And also what I always like to have is I like to have like a simplest working prototype of a method before I try to then discover all the other beautiful ways of thinking about the same objects. So essentially, in the end, what I said, since this is a boot camp, and I hope I will be around, and I hope many of you will be around as well, and we can sort of continue into the more advanced topic later. What I wanted to do here is I just wanted to give the lecture that I wish someone gave it to me 7 years ago. So just to get you started. So essentially, what I want to do is somehow I want to introduce a bit of redundancy with like what Steve did. So essentially, I will do the same thing as Steve did, just differently. And somehow I will try to give you like the self-contained proof of square root of m. So this is essentially was the best bound we knew up to until a couple of years ago for interpret method, from basic principles, essentially starting from just you have to know a little bit of analysis. Like I think this will be something that I 7 years ago would be able to understand. So so hopefully this will be a low enough bar that everyone will be comfortable here. Okay, good. So let's get started. So essentially, this is all, let's start at the very beginning. Continuous optimization is essentially a study of one simple problem, namely unconstrained minimization. So imagine we have some function f, and let's assume here that f is actually, first of all, smooth. Okay, and also, let's say it's actually strongly convex, and I will explain what strongly here means. Okay, and I hope we all know what convex means. And by the way, this is a crash course, so I essentially will go on the critical path to what I need. And along the way, I will assume away or will sort of ignore a very important subfields of the field. In particular, both these assumptions are actually sort of strong assumptions. And there's a whole beautiful theory of how to deal with the case when this is not the case. And there are very interesting cases. But I will just focus on what I need for interpret method. Okay, so we want to minimize the function f over unconstrained domain, and we know that function is smooth and strongly convex, which again I will explain what exactly strongly means in a moment. So how would we go about this? Well, continuous optimization is a science of iterative methods. So what we would like to do, we would like to start with some solution x0, and then somehow have a way of refining it to a better, increasingly better solutions, the step by step. So in general, we just want to find a way of, I have some solution xi, and I would like to have a method of refining it to get some better solution in xi plus 1, okay? And that's essentially the basic, the basic scheme for most of the continuous optimization here, okay? Now, the question is, how do I do that? So how do I perform this very basic step if I want to minimize such a function? And this is already what Steve already said. So in a sense, there is only one principle in continuous optimization, and what it says something is that no matter how complicated your function f is, as long as it's sort of nice, if you look close enough around the point, it's always essentially a linear function. Okay? So essentially, all that you really need to know in continuous optimization is really Taylor theorem, okay, which tells you that if I have some point x around which I want to understand my function, how it behaves in the neighborhood, and essentially I can write, so I have point x, and then there is the point that I would like to understand, which is like some x plus delta. So then I know that I can write f of y as the value of the function at the point x. This is the like 0th order term. Then there is the first order term correction. Okay. Then there is the second order term correction, where here we have the Hessian a Hessian of the function. Okay, and then there are many other terms, and I can just write these terms, for however long I want. They will depend on the higher orders of the function. Okay, so this is Taylor expansion. It tells me that this really I can understand the function, the value of the function everywhere by just looking at this at this expansion. And somehow the interesting terms that are the most interesting here for continuous optimization are just the first two, because this function, let's call it f hat of x of y. This is the function that is parameterized by our point x, and it of course varies over y. But the nice thing about this function is this is just like the simplest possible function. It's just a linear function. So sort of like the crucial insight of continuous optimization is that like every function, once you look close enough, and I will explain why close enough in a moment, it just can be viewed as a linear function. And then over here I have some kind of tail. Let's call it f tilde of x, which essentially essentially this is the error term. This is the tail or the error of my approximation of the function by this linear function. Okay, so somehow clearly all these terms here are at least quadratic in my deviation. So essentially, as long as I am the point y is close enough to x, sort of this approximation, like this error, is small enough compared to the to the approximation that we get. So essentially, if I look at the close enough neighborhood of my point, the function is essentially linear. Okay. And once I know that my function is essentially linear, it's very easy to see how to improve, like how to locally improve my guess. All I do is essentially I just think, okay, if I'm at point x, and this will be my point xi now, then I just want to reduce the value of this function the most. What is the direction that makes it the most efficiently? Well, essentially I just need to, this is my displacement, I just need it to be exactly in the direction of this vector. So essentially this told me that I should always move in the direction of the minus gradient. Okay, and that's exactly the whole principle behind the most important algorithm in continuous optimization, namely gradient descent. Okay, and the algorithm is very simple now. So we start with some x0, and then we just repeatedly refine our guess for how many times we want by just taking xi plus 1 being the old point minus eta times f of xi, where eta is just some scale that just says that how much do we move in a given direction. Okay, but this is the algorithm, and this is the reason why we expect it to work, as long as this eta is small enough. Of course, now the question is what the eta should be and what should be the convergence bound. Okay, and essentially, clearly on one hand, we want eta to be as large as possible because we want to make as much progress as we can. On the other hand, we know that the moment this eta is large, then somehow this approximation becomes inexact, and somehow this tail error essentially starts to kick in. So there is some uneasy compromise between these two things, and that would exactly will govern our choice of eta. Okay? So what we need to happen now to understand the convergence, what we need to understand is actually understand how does this tail behave as a function of distance from our initial point x. Okay? And the most common way of doing this is essentially via properties called smoothness and strong convexity. So essentially what you would like to say, that for every x, okay, and every y, what you would like to do, well, here's our tail. So here's our tail. What you would like, well, you would like on one hand to upper bound it by the simplest possible function that is like essentially not linear, namely quadratic. So you would like to put that this is at most some beta over 2 times displacement. Okay? And then we also would like to lower bound it, so we would like to sandwich it between these two quadratics. Okay? So essentially, this parameter over here is called alpha. It corresponds to strong convexity. And I will give you geometric intuition in a second. And this parameter over here is referred as smoothness. So sort of they are actually like quantitative way of talking about smoothness and strong convexity. So somehow pictorially what you want to say, just want to say the following. So imagine we have our function f. This is our function f. And now we look at this function around some point around some point x. So what do? Well, we look first at this linear approximation, which will be just the line that is tangent to this thing. So this will be our function f hat of x of y. Okay, but now again, we want to understand this error term. And essentially what this allows us to say is that we can sandwich the behavior of this function, which might become quite complicated when we move far away, by these two quadratics. So one of them is this, this lower bounding one. Okay, and the other one is the upper bounding one. And sorry for my poor writing skill, but this is supposed to be a quadratic. Okay, sorry.
No. So like the upper bounding one looks like a really tight U. The lower bounding is super wide. It's okay, but like that won't work.
What will not work?
I mean, it has to be super sharp. The upper bounding one is super sharp. Don't worry.
Well, it works at least here, right? So it's.
Topologically,
these practitioners, they actually know how quadratics work. Yes. So. Anyway, I hope you got the picture, and my poor skills at writing quadratics, it's one of my many poor skills, so please forgive that. Okay, but this is the principle, this is the idea, and the moment we now understand the behavior of this complicated tail in terms of this lower bounding simple function, the quadratic, the lower bounding quadratic, and the upper bounding quadratic, we can actually analyze, the trade-off between the progress made by this linear approximation and the error introduced by this tail, essentially as a function of like how much we move. And when you put all of this together, and I will not do that, but this is actually quite simple, what you can prove is that if you want to get an epsilon approximate solution, okay, all you need is just number of iterations, number of gradient steps, that is O of beta over alpha times log 1 over epsilon. Okay, which is, by the way, the dependence on epsilon is very good. And somehow the crucial thing over here is exactly this ratio of beta over alpha, which is usually called the condition number. Okay, and somehow it tells us exactly, how well we are able to sandwich this tail. Okay, so when it is good, we are converging fast. If it's not so good, we are not converging so fast. And by the way, again, here I assume that alpha is positive. This exactly corresponds to this strongly part here. But in general, if alpha is 0, then there is also another bound that one can prove, which is much weaker, but still works. By the way, here is the distance of the initial point from optimum. And here you just have this over epsilon squared, I think. Good. So essentially, this is roughly, this is like a epsilon, right? Yes. It's good to have some experts in the audience. Okay. Essentially, so this is, this is the basics of gradient descent, and somehow this is the principle. And yeah, there is some math to get here, but actually this is very simple once you have everything in place. But now the question is, okay, yeah.
Yeah, here.
Sorry.
Yeah, can you give some moral explanation for why one would expect alpha to be in this bound? Because we're lower bounding the error?
Yes, so this is something I wanted to skip, but the idea is that you need alpha because essentially, can I take it offline? So essentially, I just will say, what this allows you to say is just, this allows you to relate, how far the optimal solution can be. So the problem is that if you don't have this lower bounding quadratics, then somehow you can't feel how far the optimum is. And I really don't want to go into that. I'm really happy to talk after talk. This is a crash course, so I'm skipping over anything that is not critical for the thing, but I'm happy to go into it offline, okay? But the problem is that you really need it to be able to essentially get this logarithmic dependence on error as opposed to polynomial one. So see, here you don't have dependence on alpha, and I can explain why this makes sense offline. Okay? Sorry about that.
So the error is being measured in X space rather than
the error is measured in the value space.
The value of that.
Yeah. So again, for logarithmic regime, which is something we focus here more, it doesn't really matter. And for non-logarithmic, actually, it does matter a lot. But yeah, let's not go there. Okay. So we know that, particularly in the strongly convex case, if we have good condition number, things are good. But what if we don't have good condition number? Well, so one thing that you can do, you can slightly improve this running time, and you can actually get, via a bit different scheme called accelerated gradient descent, you can actually get a square root of condition number here. That's one thing you can do. But there is also a more interesting way of trying to fight the cases when this condition number is bad. And what you essentially do, you essentially try to use a different geometry than just L2 to approximate your tail. So essentially, so far, and by the way, I forgot to write it, so far we try to understand this lower and upper bounds in just the L2 norm, so in the Euclidean norm. But actually, this makes perfect sense if we just take some, put some arbitrary norm here, okay? In principle, okay? So as long as we allow alpha to be 0, this makes definitely perfect sense, okay? And now, once you use different norm, you might get a different bounds on this because, this function might behave nicely in some other norms. And this is often the case, in particular for max flow, this is the case, and for many problems, you can choose the right, for max flow, the L infinity norm is the right norm to look at. For minimum cost problem, it's L1 norm is the right norm to look at, and in the right norm, this kind of this value of beta actually can be much smaller than what we would get if we work in the Euclidean space. Okay, there is just one note that once we move from the Euclidean norm into a general norm, then actually our gradient state changes because now we don't merely move into the direction of gradient. What we actually have to do, the most efficient way to move is in the direction of, I would call it gradient hash, which is just defined as the direction that maximizes the following thing. So this is just the inner product. I will explain in a second what it is. It might look scary, but it's actually very simple. Essentially, what we are looking is that we want to choose a vector that minimizes, that pushes this term as much as possible, but somehow our currency is the length of this vector in the whatever norm we are working with. So if I put Euclidean norm here, then the best direction is just to go directly in the direction of the gradient. But if it's not an Euclidean norm, then actually this might be some different direction. And that's left as an exercise what it is, for instance, for an infinity norm or L1 norm. Okay, but this is the only modification you do. So essentially, you put just this over here. You just put this hash, and then you have an algorithm that works for a given norm.
No.
Is there a square on the dot product?
He's assuming square norms.
Sorry, what am I assuming?
The square. Why is there a square?
But there should be a square, right? Because that's how we bound it here. Yes.
You always bound it with square norms.
Yes, because essentially we're just saying, essentially we know that the extent of the tail depends only on the square of the norm of the displacement. So that's my sort of currency. I want to trade off, how much length I have towards how much mileage I get out of this direction.
Does the first term have a square?
The first term doesn't have a square.
Second term.
Yeah, just this. That's just the second one. So again, this is the progress we get from over here, and the other thing is penalizing us for whatever tail we are. Sorry?
I think you need a square of the second term.
What is the?
That is a square.
I think
There is a square here.
No, but even with that part is implicitly a square because
It's implicitly a square because notice that here we have one vector times the other vector. So in the end, it's proportional to the square. So this is something that depends on the square of the length. Okay? Good. So that's great. So that's that sometimes gives you a mileage, but actually it turns out that for some problems you can come up with the right norm just because you understand the problem, but also there is somehow the generic, the best possible choice of the norm that you can imagine, and essentially the best possible choice, but there is a caveat here that you can imagine, is to consider so-called local norm. Which again sounds scary, but actually isn't. So a local norm of a vector is essentially just what I do is I just take the Hessian of my function at point x. So it depends on the point x I am actually evaluating it. I just take the Hessian of my function, which is if it's strongly convex, it's a positive semi-definite positive definite matrix. So it gives me a scalar product. It gives me a metric as well. And I just exactly look at the, at the length of this vector with respect to this metric. Okay? Why this is a good norm to choose? Well, the idea here is that exactly the square of this norm is exactly this expression. So in particular, if I look at, if I take v to be y minus x, then exactly I can just do some pattern matching. That what the term I will get here will be exactly the first term that I get in the Taylor expansion. So again, as long as my as my displacement is not too large, this term will dominate the whole tail, and because of that, I will actually get a very good close to 1 ratio of beta to alpha. Actually, it will be alpha and beta will be close to 1.
Or exactly 1.
Or exactly 1 at the very but then they sort of degrade. So so this is great because once I use this local norm, then I get like a very tight upper and lower banding on my tail. But there are caveats. But we will get back to it. Just for now, we'll just think, okay, so if I use this norm, what does the gradient, what will be my gradient step? Well, my gradient step, after some quick calculation, in this case, will be just my original gradient direction. But then I have to just multiply it by the inverse of the Hessian. Yes?
But even here, for the local norm, you would need your v to be small enough. Right?
Yes, I will get to that. So that's the caveats. For now, I'm just saying, at least when v is small, this is the best norm you can consider your gradient descent in because it very nicely predicts the tail. And then, your step then will become, essentially, I can just rewrite it. Your step will become exactly this. Okay? And this algorithm, is very natural, and it has its name, and its name is actually Newton's method. So this is exactly what Steve talked about. And again, this is a nice thing about conditional optimization that it's a nice thing and also a very perplexing thing that everything can be derived in multitude way, and you might not realize that this is the same thing. But essentially, this is the Newton's method algorithm that essentially does that. Now, there is a problem that already Jelena pointed out, that somehow I am cheating here. Because, I would like to say now, as I already wave my hand, for when I use this local norm, then this alpha and beta here are close to 1, so I have close to 1 condition number, so I can just use this bound and get super fast convergence always. Well, this is actually not so, because the problem is that this is a local norm, meaning it actually can change from point to point. And this analysis over here only works for fixed norms. So if I find a fixed norm that always have such a good tail bound estimation, I will be fine. But here is not so. It's only this good estimation only works when v is not too large. Okay? And that's sort of a severe limitation of Newton's method, because now it's actually very tricky to analyze the convergence. So essentially, if it happens that our initial point is close to the is sufficiently close to the optimal point, namely it's sufficiently close that our local norm is still, at this starting point is still good a predictor of the local norm at this optimal point, then things will happen very quickly and very nicely. Except if it doesn't happen, then it's not clear what in general will happen. So you can try to analyze what will happen, and it becomes a bit nasty because what you have to do then, you essentially have to sort of bound the third order moments of your Taylor expansion in order to to understand how bad your error grows. But yeah, this becomes messy. Okay, so that's one thing to remember, that Newton's method, as natural as it might be, is actually quite nasty to analyze for global convergence. Okay, so it's not really possible. Well, it is possible, but it's hard to get this kind of bounds for it. However, there is a saving grace, namely what turns out is that actually Nesterov and Nemirovsky, they actually identified a broad class of functions for which you can have a relatively clean analysis of Newton's method. And this class of function is called self-concordant functions. And I will not define what they are because that's actually is in a sense not really important for this for this talk. But what is nice is that if your function f is actually self-concordant, which essentially involves some condition that allows you to bound the third order moments in terms of the second order moments appropriately, then suddenly you can actually get a global analysis of the Newton's method. And again, I will not cite what are the exact bounds you get. I will just need one important fact, namely what we have when our function is self-concordant is that essentially there is a certain important quantity that we just will define, which is called Newton decrement. Okay, and essentially it is just defined as I take the gradient of my function, then I will write the expression, I will explain what it means. Okay, so essentially what it is really, well, one way to look at it is, it's just I just take the gradient, like essentially I measure the length of the gradient subject to the norm that is given by the inverse of the Hessian. So here in local norm I had the non-inverse of the Hessian. This is the inverse of the Hessian, and you can actually know that what it really is, that if you want to sound cool, it is actually the dual local norm of the Hessian. Okay? You can also view it as a local norm of this step. So essentially, this is the local norm of the Newton step. Okay, and again, there's a couple of other nice things that you can say about this. But actually, all I really need to know that you get out of the analysis of the Newton's method for self-concordant functions, and that's the only thing I will black box that actually will be needed to get everything I want to get, is that there is the following fact. If I look at my point, and if the square of this decrement is at most 1/10, okay, then a Newton's method converges very rapidly. Okay, and by very rapidly, what I mean by very rapidly, I mean that it converges in log of 1/epsilon iterations. So it's not log of 1/epsilon iterations, it's just like log of log, or as some books say, it's at most 6. Which is, I guess, a reasonable bound.
So it's d squared, right?
Sorry?
So it's 6d squared.
Yes. Okay, I will not go on this, especially. Yeah, but like this is actually like essentially. Okay, I will not be baited into this conversation. So essentially, so this is just something. Essentially, we can assume that the moment we get a solution x for which, for our self-concordant function, this is at most 1/10, we know that we are done. We essentially get, we get the optimal solution for free.
But why 1/10? Why can't you have any constant?
Because there are some constants there, and 1/10 works. 1/4 will also work.
Yes, it's small.
It's small, like it's sufficiently small constant, and you can actually, depending on your definition of self-concordance, you can, yeah, you can get one, because. Yeah, so okay, essentially, if you, I am happy to talk about it offline, but essentially the thing you can prove is that your new decrement, which is also your measure of error, is at most, I think what you can prove is something like that. So essentially, you square your old decrement, that's the boundary of your new decrement. So if this is sufficiently smaller than 1, then you will make progress. But if it's larger than 1, then actually you are diverging. So essentially, this is only helpful when this is sufficiently small. Yes?
So I got confused because we were talking about global convergence, but this sounds like a local convergence.
Yes, yes. So and that's again one of the things that I'm allowed to do because it's a crash course. But no, what I'm saying is, so one thing is that if you don't know that the function is self-concordance, if you just do this with like eta equal 1, you might not completely diverge. The nice thing that self-concordance gives you is that actually you always will converge to something. But additional bonus, and that will be the only thing that we really care about, is that once you are sufficiently close, you have this very rapid convergence. But like Newton's method will converge always, and that's actually not, that's not typical. Yeah, there is damping, but that's already cheating. Yes, then you are there's starting to play some tricks.
You get global convergence with self-concordant functions
think you need damping factor.
I don't think you need.
Yeah, you do need the damping.
You don't need the damping function.
If you're outside of that domain, then
No. If you're outside, then you don't need it. I think you still. Oh, okay. Anyways, the point is, good things happen. I'm pretty sure you don't need the damping function. We can take it offline. Anyways, in the end, all I need is just this fact. Actually, like all I wanted to say up to now is just to get this conclusion. And now I can just tell you I interpret my method with like essentially the best bound that were known up to a couple of years ago. Okay.
Just to make clear, so if my starting point has this property, then I converge quickly?
Yes.
Okay, that's it.
That's a very simple thing. It's just like
No, that's not true. I mean, it has to be. You have to guarantee that in the whole region around the optimal solution.
no, that is
no.
That is
Once you have this, you actually that's the whole point of self-concordance. You actually know that your new point.
Okay, sorry, you're assuming self-concordance.
Yes, self-concordance is very important here. No. That's okay.
I think it's worth mentioning that the whole point of self-concordance is that it allows you to quantify what the local domain of convergence is.
Yes.
Yeah,
That's everything is true. Again, it's a crash course. I did exactly this kind of all these tangents are beautiful. I enjoy them, but I think if you hear it the first time, you just want to hear this information.
It's really important because normal Newton's method, if you can guarantee that in a
Okay, let me give the course the way I want it, and then you can give your. No, I agree, but this is exactly like you read these books and they are beautiful, but they go on all these things, and by the time they are finished with the tangent of why you do here, you already lost the train of thoughts. Okay, I want what I promise you is this the shortest path to the interpret method. That's what I'm giving you, and for that you don't need to know why this is the case. You just need to accept this fact.
This is a fact. Okay, so sorry. So just recapping for the ignorant people one more time. Okay, so if my function has a self-concordance property, and I have my starting point having this property, I will continue to have this property forever, and then I convert.
The property is independent of the starting point. The property is the property of the function, and what is true is that once you have the property of this function, which will be the case.
The squared property. This is the property, right? This is the property.
Yeah, this is the property, yes, and then you know that it will hold to like yes. Essentially, what you will have is exactly this behavior that your new point will it will be smaller. So essentially, if this is smaller than 1, this will also be smaller than 1. Okay, and that's the only thing you have to know about Newton's method. Did they offend you greatly or only a little bit?
Or like for the crash course, is it important that it's log 1 over epsilon as well?
No, it's 6. It's 6. Come on, you're not reading it. It's 6. And that's not important.
And log 1 over epsilon would be fine.
It's log 1 over epsilon would be fine. The point is that if you have this condition, you are done. It's like you have an optimum solution. Okay, great. So that's really all I really need for you to remember so far. But I wanted to motivate this fact so at least you have some idea where it's coming from. Now we can actually do something useful and solve a linear program. Okay, so imagine that I want to solve a linear program of the following form. Okay, so without loss of generality, every linear program can be cast like this. This is like a dual, essentially, form of the linear program. And I did the evil thing, and I changed the notation that Steve used, and essentially, I just there is some renaming of the vectors that would get you back to his regime, but it's not really that important because you can definitely believe that every LP can be cast in this form. Okay, and now the question is, how would I go about solving this this problem? Okay. So as already Steve mentioned, somehow the first trick you want to do is actually dealing with inequalities is quite hard when you want to do it explicitly. So what we do, we cheat, and instead we try to get rid of these inequalities by changing the objective functions, somehow incorporating them into objective functions we are optimizing. So what we will consider instead, we'll consider the function f mu that has, of course, the original cost function that we had, but then divided by mu. You already have seen it in Steve's talk. Okay, and then we have this barrier function, which essentially what it has one term for every inequality here, and it's the logarithmic barrier. So essentially, what it does, it just looks at at the jth constraint, and it penalizes. If it's getting if this thing is getting close to being invisible, then essentially this shoots up and somehow tries to repel us from there. Okay, So essentially, so as long as I am, start from some point that is feasible and I try to optimize this function, I will be naturally repelled from ever crossing into infeasible region. Okay? So from now on, essentially, what has happened is that essentially what you can observe is that, okay, there are two observations. So one observation is that actually, if mu is large, sufficiently large, then I can solve. Okay, so sorry, let's introduce some notation before I talk about observations. So let me define x mu star as the optimum solution to this, to this function f mu. Okay, so this is just argmin over x of f mu x. Okay, this is an unconstrained minimization problem. I can just define. I just define the optimum. And of course, it will depend on mu, right? Because we have this factor mu that trades off our cost function we would like to optimize versus this barrier that is just making sure that we are not getting any infeasible point. Okay? Now, two observations that we want to make is one is that actually you can get x mu star for sufficiently large mu. So essentially, if mu is large enough, magically, and actually Steve explained how you can do it, you can actually get this solution right away. Okay? And then the other thing that is actually important for us is essentially if I look at the limit of mu staying positive but approaching 0 of these solutions, okay, then essentially this will become the optimal solution to the original LP I wanted to solve. Okay, and the more precise way of stating it, what you can show is that the cost of your solution x star mu compared to the cost of the best solution is at most mu times m. Okay, when m is the number of constraints. Okay, so clearly if I get mu sufficiently small, I can get arbitrarily close to the to the good solution. Okay, so that's great. So now all I really need to do, I need just to minimize this function for sufficiently small mu and be done with it, right? And I already have methods for doing it. So one way to try to do it is just like let's apply gradient descent to it and see what happens. And it would work. Except the problem is that if I look at this function, it actually is strong convex in any reasonable setting. But the value of alpha, the condition number, might be essentially arbitrarily bad. So we would solve a problem, but it would take a long time. So that's not satisfactory. So somehow we would like to have a bounds that do not depend on this kind of how good alpha and beta is. So what do? Well, we would like to use Newton's method instead. Okay, we would like to essentially use gradient descent on this function, but in this local norm given by this function. Okay. But now, the problem is that, as I said, Newton's method actually is not that a great method for minimizing the function if we just start from an arbitrary point. What we actually need a good point to start from to have a hope that we actually converge quickly. Okay? And that exactly is this kind of, that's where the idea of essentially interpol method and also central path following interpol methods comes in. So what I will do, well, I will not try, so the one thing you could try is just, I just get some starting solution for mu being large, and in one shot, I set mu to be small enough for me, and just use Newton's method to converge directly to this thing. That will not work in general, because again, this solution, this initial solution I get might be very far from the solution that I want to get. So what I do instead is I just try to, slowly convert, slowly chase the point I want to do. So a little bit of algorithmic intuitions. And again, Steve already essentially drew this picture, but let me draw it again. So essentially, if this will be our, the feasible region, defined by our inequalities, okay, and let's say over here our cost vector is over here, so our solution is somewhere here. What really happens is that if I take mu to be large, or let's say infinity or close to infinity, then this optimal point x star mu will be something called analytic center of this polytope. Okay, something in the middle that tries to stay away from all the constraints as much as possible. Okay, but now essentially as I make mu smaller and smaller, what will happen is like I can look at the solutions that I get. I will get a curve in this feasible space that is slowly approaching this optimal solution. Essentially, as I'm turning off the barrier like more and more, I'm getting closer and closer to what the minimizing of the cost function is getting me through. And essentially, all I want to do here is instead of the first idea would be just start here and try to converge directly to this point over here. That will not work. So what I do instead is I just have a moving target. So essentially, what I do, I start with the initial point, then I find some. I don't try to get all the way here directly. I try to get here to some point x star mu prime for some mu prime that is 1 minus delta times mu. So there's just something that is just slightly smaller mu, but not too drastically smaller. Okay? And I hope that this delta will be small enough. On one hand, it should be large because you want to make progress, but on the other hand, it will be small enough that actually this new point x mu prime star will be close enough to x mu star, so I actually get the rapid convergence. So essentially, that this solution is within the rapid convergence radius of the of the Newton's method. Okay, that's the whole scheme. So sort of, I would like to essentially have I try to follow this curve by just this discrete steps using Newton's method, and that's exactly the whole scheme I want to do. Clearly, this will work. The only question is, how large delta can I put here for it to make it work? Because there is always sufficiently small delta for which this will work. Because for delta equals 0, this is the same solution. So clearly we have rapid convergence, and there has to be some positive delta for which it still will be within the radius of rapid convergence. The question is, can we lower bound how big the delta is, so as we always are guaranteed that we will be close enough? Okay, that's the only thing that is left. Essentially, once we said that, if we have some lower bound on delta, then we know that our total number of iterations will be delta inverse times log 1 over epsilon. Okay, so essentially we'll get an epsilon optimal solution after there will be m here after this many iterations. If we have some absolute lower bound on delta, yes.
Why do we expect to be able to multiply it instead of
That's a good question. As you will see, we will be able to do it. Actually, we are able to get this multiplicative decrease. In principle, this is without a lot of generality because there is definitely some positive delta for which this will be true. But it turns out that actually you can get a multiplicative decrease like that. So this is not obvious why this should be, but this is what we want if you want to have the kind of logarithmic dependence on error. And as we will see, actually you can get that.
What is this error?
Sorry?
What does epsilon refer to?
Well, essentially, I want mu to be epsilon over m, right? So essentially, I get that this is at most epsilon. So this will be just the error in the value of my solution.
Yeah, the multiplicative decrease is what puts me to the self-concordance property for the barrier.
Yes, but again, it's a crash course. I don't mention this wall. Again, I'm just telling you what I hope you need to know to just get the shortest working proof of it. And then we have the rest of the semester to discover all these beautiful connections and the beautiful views on that. I don't know. Maybe I am a bit going against your tastes by doing this, but that's how I learn. And just wanted, maybe some of you are similar to me, so that's how I do it. If you are disgusted by my ignorance and barbaric presentation, I'm sorry. Okay. This is recorded, right? Okay, good. Okay, so is everything?
So just one quick way you can see why the multiplicative decrease is a good idea. The ax minus b is if you are going to change by some constant factor, if you change the u by some other factor, and that log is only accurate. The second order approximation of the log is only accurate when those ax minus b is changed by that factor.
Yes, that's all true, but I just don't want to go into it. But hey, that's a very good intuition. But yeah, in the end, we don't need to know. So definitely we can write it like that, and then magically, as we will see in a moment, we will get this bound. You can figure out why you expect it to happen. I just prefer to do the show not tell or whatever is the meaning of it. So I just prefer to have a proof and then see, and only then in retrospect see where did it come from. Okay. So essentially, what do I need to just analyze? I just need to analyze the following, the following situation. So imagine, I have a solution, optimal solution to my problem for some value of mu, and I want to understand, how big can delta be, while still guaranteeing that this, the optimal solution to the new problem for the new mu prime is still close enough to the solution, so I get a rapid convergence with Newton's method, right? This is all I need to do. But now I exactly know what is the math I need to do to compute that. Because what does it mean? So by the way, logarithmic barrier is self-concordant. Actually, this is very important. So that's I guess part of the whole reason why we put it there in the first place. But so now I can just essentially apply this fact to it. Am I saying something wrong?
Well, not according to your definition, right? You have to scale it or something.
No. It's actually.
You don't get the 1 over 10.
I don't think he defined self-concordant.
I didn't define self-concordant. That's a good point. Yeah, but that's something that you have to show. Like essentially, you have to believe me that the logarithm function is self-concordant according to the right definition that makes this statement true. Good. So for now, there is nothing to like. Now I have to analyze this Newton decrement and see if it how big delta can be while still satisfy this. That's the whole question. Yes? So essentially, what I need to do now. Yes. So essentially, okay. So what I need to do, and this is very simple now. Really, a bit more technical, heavy lifting is in this fact. So what I need to look at, my Newton decrement with respect to mu prime, because I'm minimizing the function f mu prime. At my initial point, that is x mu star. Okay? And I would like to see, I would ideally look at the square of it, and I would like to show that this is at most 1/10 for some value of delta. Okay? So I just want to look at this quantity. What is this quantity? Well, we know from definition that this is exactly the gradient of mu prime at the point x mu star, the Hessian mu prime at the point mu star inverse, and again the gradient. Okay, that's exactly the quantity you want to bound. So let's look at it for a moment. What it is exactly. Well, this is actually just an exercise in taking derivatives. So I will spare you. So let's just think. So what is, yes?
The thing you have in the box is lambda. Is that lambda or lambda squared?
Here is lambda. Oh, sorry. Yeah.
Yeah. Okay. Good.
So essentially, okay. So first of all, what is the gradient of f of mu for a given mu and given x? Well, after a little bit of computation, you will know that this is c over mu. So this is just this is the first term that you get, minus essentially a transpose times s, and I will explain what s is in a moment, times all ones vector. So what is s? Well, essentially for every inequality, I define the slack. So what is the slack is essentially this is aj transpose times x minus bj. So essentially this says, how far I am from violating given inequality. So I have such a number for every inequality. And now essentially the matrix S is just the diagonal matrix where each entry, it's an m by m matrix where each diagonal entry just corresponds to exactly the value of the slack. Okay? And then I take an inverse, so essentially this is the inverse. Okay? So this is the gradient. And there is a nice way of writing this essentially as a hat transpose, where I just have a shortcut. A hat is just the s minus 1 times a. Okay, because this expression will show up a lot, so I just want to shortcut it. Okay, that's the gradient. Now, what is the Hessian? The Hessian, well, this is a constant term, so it essentially goes away. And what you get out of the Hessian is that essentially this is a hat transpose times a hat. Okay, so that's what you get when you compute what is the Hessian. So essentially, you can see that the Hessian is essentially sum of rank 1 matrices, where each weighting is with S is just 1 over the slack squared times the corresponding rank 1 matrix corresponding to the row. I guess this is here. Okay. So in particular, this shows us that indeed this function is positive semi-definite, as long as these things span. This is full rank. But yeah. Okay.
But S is a function of X, right? I mean,
yes, S is a function of X, and I'm suppressing that because the notation will be very unwieldy. Yes, that's very important. S is a function of X. So in particular, that's why I here have hidden S2 minus 2, because actually I have to differentiate it as well. Okay? So far, so good? So yeah, so essentially the way the Hessian depends on X is exactly via the slacks which change, because the matrix A is the same. The only thing that changes are the slacks. Okay? Are these weightings over here. Okay? Good. So now we can essentially evaluate our thing. So first of all, I want to evaluate what the gradient of mu prime at the point x mu star is. Well, what is it? Again, I can just use the definition. Okay. So mu prime is 1 minus delta times mu, and then the rest of this is the same. And again, this A, essentially, this A is given by this solution. Okay. Notice that the only thing changes is essentially this. Okay. Now I will just cheat a bit because I just don't want to deal with the exact math. So the way I can write it, I can just write it as a C, like delta times C, right? Plus the gradient of f mu at the point x mu star. Okay, because essentially, if I had c mu over here, that would be exactly the gradient of the function f mu at this point, and then I get have one minus delta. So essentially, this gives me a term that is roughly behaving like over mu. Yes, of course. Thank you. Okay, but now the question is, what is that?
Zero.
It's 0, right? Because we know that we are minimizing the function f mu, and we are at the optimal point, so clearly there is no way of improving it. So this is always 0. Okay? Now, so essentially we get here that this is roughly delta C over mu. And actually there is something more that we can say about this. Essentially, since we know that this gradient is 0, it also means, if I look at the definition, that C over mu is equal to A hat transpose times all one vector, right? This is just what it means for this gradient to be 0. Okay? So essentially what it means is that this gradient that I have here is exactly delta A hat transpose times 1. Okay? We are almost done. So I can write now that the thing I want to estimate is essentially, I will just pull delta squared in front of it. And now I just have, I have A hat transpose all one vector transpose times A hat transpose A hat minus 1, A hat transpose all 1. Okay, that's what I want to evaluate. I mean, this is a very cool interpretation, but I will not go into it. Sorry about that. I just want to understand, how large can this be? Okay, because once I know how large it can be, since I in the end want to have this to be at most 1/10th, it will tell me, how small delta has to be for the condition to happen, right? So that's the only thing, is to bound this thing. But now, if you know a little bit of linear algebra, you know one trick to evaluate this kind of stuff. So essentially, one nice way of doing it is if I want to evaluate how much such equation, like how much, how big is such equation is, all I have to do is essentially, this is exactly I can write it as an optimization problem. Okay, so this is.
It's the projection operator. So
I know it's projection operator, but let me. I might not be very well versed in continuous optimization, but I know that much. But that's not the point. It's.
Isn't the a hat for mu prime?
No, a hat.
I'm sorry, for mu.
A hat is for mu. Yes, a hat is for mu. Now we got rid of mu prime. There is no mu prime anymore.
But isn't the middle like the? I thought that the Hessian was for mu prime.
No, but the Hessian depends. It doesn't depend at all on mu. It only depends on the point, and the point is x mu star.
Okay.
Yes. So the only thing that changes depends on mu prime is the gradient, and then there is mu prime here. But the matrix A depends on the point that you are at, not at the value of mu.
Okay.
Okay. So they are all the same. I'm not cheating here. They are all the same. They are the same matrices. And essentially, I can write it as just the minimum over all the vectors of essentially the norm of the vector, subject to the constraint that z. There is such that b times z is equal to v. Okay, so essentially I can view it as an optimization problem when I want to optimize over z. It's just 5 more minutes. You will survive. I hope. This heresy. Essentially, so this is the variable z, and essentially the optimal solution to this problem is given by what we exactly want. Just so I don't get the. It's just by b transpose b transpose b minus 1 bv. Is that correct? No, it's without b. Okay, that's the solution that you get, and then you will get exactly this. But somehow the point here is that this is a minimization, and this is the optimal solution. But if I choose any z here, I will get an upper bound on this quantity, right? This will give me the best upper bound, but any upper bound will work as long as I satisfy this thing. So essentially, now let's apply this thing to our problem. So we have delta squared, and now essentially I can upper bound it by z, the norm of z for any z such that what has to happen? Well, a hat transpose z has to be equal to the a hat transpose all one vector. Okay, I just translated this. So any z that satisfies this, its norm will be upper bound on this quantity. But now there is a very easy upper bound. It's just a pattern matching. I just take z to be all one's vector. Clearly, this will be equal, and the norm of this will be at most delta square times m. Okay, and that's always will be true. So now what it tells me is that as long as delta is at most 1 over square root of 10 over m, okay, actually this property will be satisfied, so I will converge. Okay, that's it. We are done. Okay, this just tells us that essentially setting delta to this quantity will make the whole scheme converge, and the final bound we will get is essentially O tilde of square root of m log 1 over epsilon, which is, by the way, the result of Renegar. I don't remember the year, but okay. That was it. You now know how to solve linear programs. In essentially, this was, and in a sense, it still is the best time we know. So let me take this minus 5 minutes.
Don't actually. How do you initialize?
Yeah.
You are. Steve told us that. Okay. So yeah. So that's the more technical part. What you do, one way to do it is just brute force. Essentially, what you do, you essentially brute force your LP by just setting it up in such a way that it has, you can get just the solution for x mu, and just just add some penalty for whatever. Like you just add new variables and you penalize them. So in the optimal solution, they are equal to 0, and you set up things that you get the optimality conditions for this thing for some value of mu. In many problems, there's actually a natural way to do it. Yeah, so that's one point that I'm cheating.
You're on the percent, right?
Sorry?
You're on the percent.
Would it work, actually? Okay.
It's actually like, in the non-separable case, it's like adding.
Okay, good. So anyway, so this, I didn't tell you exactly how to initialize, that's true. But I tell you that this is not the difficult part, and I didn't tell you the analysis of Newton's method for self-concordant functions. But modulo these two things, you know everything now that there is to know about getting the integral method. So let me just say two things about what lies beyond it, and Aaron will talk more about it tomorrow. So now we got this bound, and the question is, if you remember, Steve said that in practice, this Newton's method seemed to, at least the right implementation of Newton's method seems to take not more than 50 iterations. Here we have square root of m. Clearly there is some slack, and I think the overwhelming belief is that the square root of m is not the right bound. So how could we go around trying to get something better than square root of n? Okay. So essentially, what has to happen is, well, one way to, maybe that's something that Aaron and myself and others are currently exploring, is essentially to re-examine this fact. Okay, and figure out, so clearly this condition is sufficient for fast convergence of Newton's method. So if you have it satisfied, everything is great. This condition essentially corresponds to like this Newton's decrement squared is exactly, it's exactly the L2 norm squared of this optimal solution. Okay, so that's essentially what it's saying, is that if this L2 norm of this optimal solution to this projection that we are computing here, if it's, essentially if it's at most 1/10th, I know I can, I will have rapid convergence. However, if you look more closely into the proof, you realize that actually, okay, let's see, you can put L4 norm here, and the proof still will work through. Okay, so essentially what you can show is that like just having L4 norm being at most this will be sufficient. And that's actually fundamental, because of course we know that the L2 norm is always, sorry, the other way around, is upper bounding the L4 norm. But now so what might happen is that L2 norm is large, but L4 norm is small, and you can still have rapid convergence. So essentially this is a sufficient condition, but not a necessary one. And of course, in the worst case, these two norms are equal or close to equal, and this corresponds to the cases when one of the components in this projection is very large. But this is only the worst case, and maybe this worst case doesn't happen. Unfortunately, it does happen. But what you can show then is that maybe there is a way of massaging your problem, so these bad things do not happen too often. In particular, the crank that you end up trying to pull is essentially here. Here we just essentially weighted each of these logarithmic terms the same, with the same weight. We just have a weight of 1 here. What you can do instead is you can put some weights here and somehow weight different, you want to weight different terms differently. And this actually makes sense, because imagine that I just take my, my linear program, and now I just like multiply, I take one constraint and put it 10 times into my LP. From the point of view of this method, this actually will suddenly boost this particular inequality more. Well, it shouldn't, because it doesn't change the geometry of the problem. So it says, so what it hints at is that actually there is, maybe a better weighting of this barrier that leads to a better behavior in the context of, of this condition. So that we don't exactly know how to show that there is a one weighting that actually gives you a better, better behavior in this L4 norm. What we can show is that there is a way of manipulating this weight as you go to ensure that, often enough you have this L4 condition satisfied, even though L2 condition is not satisfied. Okay, and essentially there are two types of results that emerge from them. So one of the type of result is essentially shows that when you apply this thing, so what you can do, you can take an integral method, and you can solve the corresponding LP in m to the 1/3 log 1 over epsilon iterations, except as you go there, to achieve that, as I said, you need to change these weights. And this actually, when you want to do with just brute force, you need to perturb your cost vector. So in the end, you can solve any LP fast, except this is the LP you solve is not the LP you started with. So this is of limited use. Still, it turned out that for certain specific problem, most notably max flow and maybe shortest path with negative length arcs, there is some way in which you can control exactly how you perturb this cost vector and what is the impact of this. And what you will get out of that is the running time when actually each iteration will just work in linear time. A number of iterations will be not exactly n to the 1/3. It will be something slightly worse. It will be something 3/7, right? I should know that, right? Log 1 over epsilon. So you will have m to the 3/7 number of iterations. And this is for actually unit capacity. So that's important, unit capacity max flow. And this is a result of me for max flow. And there is a simpler version more recently. And then the result for shortest path is the result of Cohen, myself, Sankowski, and Vladu. And this is relatively recent, and all of them are this semester, and 2 of them are actually in this room. So you can ask them about. So that's one kind of results you can get out of this. The other one, also very exciting, is the result by Lee and Sidford. So Aaron will talk, he's here, and he will also talk probably a bit about this in the tomorrow. Essentially what they say is as the following. So, so here we managed to improve the power from 1/2 to something better than 1/2, or improve, I would say. But now there's also another thing that, sort of from the theory of self-concordant function, we know that there are always barriers whose complexity will not be square root of m as we proved here, but actually square root of n, where n is the dimension of the problem. And usually m is much larger than n. Okay, and Nemirovsky and Nesterov showed a barrier that leads to such a complexity, except the barrier is not really computable. Like there is, you don't get an efficient algorithm out of it. But then, Lee and Sidford, used this idea of changing paths and sort of these insights, and he will talk about it more later, to actually make sort of this bound algorithmic in a sense, or actually very efficient. And they indeed can solve any LP in close to square root of n bounds. And there is no caveats like here that you have to perturb something. They just solve it, honestly and without problems, essentially in this Amorphous bound. And again, the point of start is exactly playing with these weights and finding the right reweighting that actually makes geometric sense. And Aaron will talk more about this. So so sorry for going over time. I'm happy to talk about anything I said during this crash course and now explain and sort of expand. I'm happy to talk about some of this following up work. I'm around the whole semester. Please feel free to approach me. Thanks.
Time for one question.
I am around. You can ask questions after.
So I have a question about the last thing you mentioned, so about this playing debate. So do we know that, at least for some structure problems, that self-concordance is really necessary, or do you think there is a possibility of playing with barriers?
I am recorded here, so I will not tell you what I think. But let's just say I think self-concordance theory is a very beautiful theory. I think it definitely is not I think you have to go it is possible, and you should go beyond the theory of self-concordance to get better bounds. In particular, in a sense, one of the results in the Lee Sidford paper actually shows that you can take a polytope for which self-concordance provably would require square root of m iterations, and they still can get square root of n by designing a more specialized barrier function that sort of are more efficient.
But it seems like there should be a way to relax it at least a little.
Yes. So again, self-concordance is a very nice abstraction. In particular, it allowed me to black box a lot of nasty calculations here. So when it works, it's great. I definitely don't think that we should look at self-concordance anymore. I think now we have to go beyond self-concordance to get some better bounds.
We're out of time.
So one of the things,
we're 10 minutes over.
I'm trying to understand what you just said, right? I mean, one of the things of self-concordance is it's not about LPs. But
Yes.
it's about
Yes.
comic
Yes, yes.
So how much of this is transferable to that setting?
I think Aaron will talk a little bit about it. I don't think that is really explored because since you can talk about John's ellipsoid, like all these things, yeah. So I don't think we really understand how much of it translates. Some of it should translate. We don't know. I think Aaron knows more than me about that. But that's a great question. That's something to explore during this semester. Exactly what does it, And this is the big, the big kind of theme of this thing is that like at first we had these insights to improve running time of LPs and improve max flow running time and something. But in the end we learned something about the geometry and about this, all this math behind this that hopefully we can export back into the theory. So I think that's a great, thing to explore at leisure during the semester.